Now we discuss some key concepts related to electromagnetic induction. Electromagnetic induction is nothing but producing EMF by applying varying magnetic field. As are seeing in the figure, this is a conducting coil. A magnet is placed nearer to the coil. Due to this magnet, some magnetic flux will cut by the coil. When the magnet is stationary, the magnetic flux cut by the coil is constant. You cannot find any current in the circuit. When the magnet is moved to and fro, as I was seeing, the magnetic flux cut by the coil varies with the time. You can find some current in the circuit. This phenomena is known as electromagnetic induction, and this experiment was first performed by Farad and given two laws related to electromagnetic induction. Before going to electromagnetic induction, first we discuss what is magnetic flux. The total number of magnetic lines of force cut perpendicular to a surface is called magnetic flux. Suppose we consider a surface S placed in a magnetic field of induction B, as we are seeing in the figure. Let ds is a small element in this surface. The normal to ds is along this direction, and this is the direction of aerial vector. From the definitions of dot product, we can write the flux through ds is d pi. This is equal to b dot ds or b ds cos theta, where theta is the angle between magnetic induction and this normal vector. And the flux through the surface, this is nothing but integration of b dot ds. This is a closed integral, and this is equal to integration of b ds cos theta, or you can write this ba cos theta. If the coil is placed in the magnetic field so that the plane of the coil is parallel to the plane, in this case theta equal to 90. Theta is nothing but the angle between magnetic induction and normal to the surface. Now this is 90 and flux to the coil is 0. When the coil is placed perpendicular to the plane of magnetic field, in this case magnetic field and normal to the surface are in the same direction, theta equal to 0, here we can write the flux is B into A. In this case, the maximum flux is cut by the coil. The SI unit of the flux is Weber, and CGS units it is Gauss centimeter square, and the dimensional formula is ml2 t minus 2 a minus 1. Now we go for Faraday's laws of electromagnetic induction. The first law is the principle of electromagnetic induction, that is, 1. A time varying magnetic flux is cut by the coil, then an induced EMF produced in the coil. And the second law is the induced EMF is given by the rate of change of magnetic flux linked with the coil. That means the induced EMF is directly proportional to d pi by dt, or we can write the induced EMF E equal to minus n d pi by dt, where capital N is the number of turns in the coil, d pi is the change in magnetic flux cut by the coil, and dt is the time interval. And this negative sign indicates the induced EMF always opposes the change in magnetic flux. This is Lenz's law. What does it mean? Suppose you consider this diagram. When the magnet is at this position, the north pole is facing the coil. When this magnet is moved towards the coil, an induced current will produce in the coil in the direction of anti-clockwise direction. That means the coil behaves as a north pole. Due to this, the magnet will be repelled. When you are moving the magnet towards the coil, we are increasing the magnetic flux, but the induced EMF that produced in the coil opposes the increase in magnetic flux. Similarly, when the magnet is moved away from the coil, the current produced in the coil is in clockwise direction, thus behaves as south pole. It tries to attract the magnet. That means when the magnetic flux is decreasing, the current produced in the coil tries to increase the magnetic flux. This is the meaning of opposing the change in magnetic flux. The Lenz's law statement is the direction of induced EMF or current in a circuit is such that opposes the cause that produces it. And this law is based on law of conservation of energy. Now I am taking Faraday's second law, and from this we are writing various formulae. Faraday's second law is induced EMF E equal to minus n d pi by dt. And Faraday's law states that the change in magnetic flux cut by a coil can produce induced EMF. And induced EMF E equal to minus n d pi by dt. This can be written as minus n pi 2 minus pi 1 by delta t, or this you can write minus na b2 minus b1 cos theta by delta t, that is E equal to minus n dy by dt b dot a. How we can change the magnetic flux cut by the coil? The variation in magnetic induction, that is the magnetic field, changes the magnetic flux. The change in area is also changes the magnetic flux cut by the coil. The rotation of the coil, that means the angle between N and B, the angle between areal vector and magnetic induction, that also changes the magnetic flux. Suppose we consider the magnetic induction changes, then we can write induced EMF E equal to minus Na dB by dt cos theta. If area changes, this can be written as E equal to minus Nb cos theta into dA by dt. And further, theta equivalent to we can write omega into t, where omega is the angular frequency and t is the time, and induced EMF E equal to minus n d by dt of nba cos omega t. If theta changes, one theta can change if the coil is rotating. In this case, the induced EMF E equal to minus nba d by dt of cos omega t, or this is equal to nba omega sin omega t. The expression for induced current is induced EMF by resistance, or this is equal to minus n by r d pi by dt. The integral form of Faraday's law is integration of E dot dl. This is equal to minus d pi by dt. Next we take the concept of motional EMF. An induced EMF produced due to the motion of conducting objects is called motional EMF. When a conducting rod or a conducting coil is moved in a magnetic field, the magnetic flux cut by the coil changes. Due to this, an induced EMF will be produced. Now we take one example. Consider a conducting rod of length L moving with uniform velocity v in a magnetic field of induction B. As I was seeing in the figure, this conducting rod moving in a magnetic field of induction B, the direction of magnetic field is into the paper, that is into the board. When this is moving in time dt, this makes a displacement dx. That means since the motion of the rod cuts the magnetic flux, an induced EMF will be produced across the rod. In this case, the induced EMF produced in the rod is E equal to d pi by dt. This is the magnitude of induced EMF, and this is equal to d by dt of B into A, and this is equal to B into d by dt, and this area, which is nothing but L into dx, and dx by dt is nothing but velocity v. Therefore, this we can write B into L into v. If the rod is moving, making an angle theta with the field, in this case, the induced EMF is written as E equal to B LV sin theta. The direction of induced EMF is given by Fleming's right hand rule. According to this rule, if we arrange our right hand three fingers mutually perpendicular to each other as are seeing in the figure, if this finger indicates the direction of magnetic field, that is forefinger indicates the direction of magnetic field, thumb indicates the direction of motion of conductor, then the middle finger indicates the direction of electric current in the conductor. Now in this case, the magnetic field is into the boat. The conductor is moving along this direction. Therefore, the current will move in the rod along this direction. That is from Q to P. The question is, the current is flowing from Q to P. Then what is the polarities of P and Q? But the polarities of Q and P are minus and positive. Why? Because this is a source. We know that the electric current flows from positive terminal to the negative terminal in a circuit and negative terminal to the positive terminal inside the source. Since this rod behaves as a source, that means it is having EMF.